talking about electric force. And you probably noticed that when you rub things together, sometimes, well, you get electrostatics. You get static charge buildup. You see this when you take clothes out of the dryer, when you walk across a carpet floor with wool socks on, you get the kind of prickly feeling. You touch a doorknob, you'll get a spark. Or maybe you want to go for your brother or sister, or jumpstart the cat. We have a name for this kind of electrical interaction. Does someone know what that phrase is? The kind of electricity we get when we rub two things together? Yes, we call it static electricity. We call it static because, well, everything around us has electrical charge, and it can be transferred from one object to another by simple contact or rubbing. But for most objects, once that charge is transferred, it does not move. We say it is static. And so for the vast majority of situations, when things are rubbed together, we are dealing with something called static electricity. The other kind of electricity is simply called electricity. That's where electric charge is free to move through material. And these materials are usually metals, and we call them electrical conductors. And unlike gravity, there's two flavors to the electric interaction. The only flavor for the gravitational interaction was mass. All mass attracts all other mass. With electricity, we have two flavors. We call them positive charge and negative charge. And things that have the same charge are going to be repelled from each other, and objects that have the opposite charge are going to be attracted to each other. So there's two flavors, positive and negative charge. And the electric force between two objects is proportional to the product of the amount of charge we have divided by their separation squared. And this constant here, this constant of proportionality, is 9 times 10 to the 9th, so 9 billion newtons per meter squared per coulomb squared. That's the units that we use to signify the amount of charge, and it's a coulomb. So two charges called Q1 and Q2, both measured in coulombs, if they're a distance d apart, the force between them is going to be the product of that charge divided by the separation squared, constant, and we got that thing there. A useful concept that we use to also describe this relation is the electric field. And that's basically force per charge. In that if you've got a certain charge distribution, say that either has a net positive charge or a net negative charge, that will either repel positive charges or attract negative charges. But it's nice to describe something that that distribution of charge can produce that we could use to predict the force on something if it was placed there, if it was nearby. And that's why the electric field is a convenient idea, in that no matter what we have, the force on a charge, we can just turn this around, that force will equal the charge times the electric field. And so we can have an electric field due to a charge distribution. And if we put a charge Q there, it would have a force. And if the charge is, say, negative, that would switch the direction of the force. So if you have, say, an electric field in this direction, that's the direction of the force that would be on a positive charge. So if we put a negative charge here, the force on it would be a negative charge multiplied by that vector in this direction, which means we get a vector in the other direction. You get an attractive force, a force off to your left. But a positive charge would mean we get a force vector in the same direction of the electric field. So talking about the electric field is a convenient way, if we have a set distribution of charge, then we'd want to ask the question, what would be the force on another charge that was placed near there? And then we have the electric potential, which is basically potential energy per charge. Again, if you've got a charge distribution, a group of charges, well, a positive charge would find a certain location to be like a high potential energy, but a negative charge would find that to be a low potential energy. So if I say have a whole bunch of charge, say right over here by the camera, that's positive. If I put a positive charge, a different positive charge over here, it's going to be pushed away. And the closer we bring that positive charge to this group of other positive charges, the higher its potential energy. Basically, we'd be having to push it towards that positive charge. And the free charge, the charge that would be free to move, would be accelerated out to infinity. We pushed way, way out. So its lowest potential energy would be very, very far away, but its highest potential would be really close. This is like being at a high altitude. But a negative charge placed in the same position would be pulled towards that charge distribution. And its highest potential energy would be very far away. Well, its lowest potential energy would be very close to this charge distribution. So again, because we have the two flavors of charge, it's convenient to talk about electric potential, which is basically potential energy per charge. In that we can have a set potential, and that would either be a high potential energy for a positive charge or a low potential energy for a negative charge. So these are convenient things to deal with, the electric potential and the electric field, just because whether or not something is a high potential energy or low potential energy will change on whether or not it's a positive or negative charge. So just for some general electrostatics, well, that's looking good. Why did you use a threaded rod? That's going to be hard to slide things along.
I think it was just the fastest one to grab.
Okay.
And the longest one.
Okay.
And these equations are in the book too, right?
We rub two things together, we could transfer electric charge. And a good standard to start with is a balloon. If you rub a balloon in your hair, well, the balloon likes negative charges more than positive charges. Basically, what we're doing is when we're transferring charge is, well, we're actually transferring particles that have charge. And what are the particles in the atom that have charge? Anyone?
I was just asking if we have those equations in the book too.
Yeah, those are, I think all of those are in the book except the equation for electric potential. And I put it there just because it's more convenient. I wrote it out in simples, KQ over D, as opposed to what the book did, writing it as electric potential energy per charge. It's really the same thing. But yes, those are all in the text. So what particles in the atom carry charge?
Like protons and electrons.
Protons and electrons. We also have neutrons that don't carry charge. So, Mr. Horsley? Crossgrove, sorry. And when you rub two things together, what you're transferring are the electrons. So when something gets a negative charge, it's because it's gotten extra electrons. When something gets a positive charge, it's because it's lost electrons. You do not transfer protons. That would mean breaking apart the nucleus, and we call that fission. You do not cause nuclear fission when you rub a balloon in your hair. Just to make that very, very clear. You're transferring electrons. And a balloon will gain electrons from your hair. And so I'm hoping I've got a kind of a charge thing going here. Do I have any sort of attraction? Yes, I thought it was attractive. And I could do the same thing with the other balloon. It can also pick up negative charges or extra electrons. And both of these balloons should now have a negative charge. And you can see they don't really like each other. They want to push each other apart. That's because like charge repels. But we need a standard. And the Greeks, all the way up through Ben Franklin, realized that we had two different charges. Ben Franklin was the first, through experiments, to hypothesize and conclude that really what we're doing is we're transferring one charge And the opposite charge is just the absence of that charge. And he freely admitted that there's no way from his experiments to tell which one was possible. And so he had a 50-50 shot and he blew it. He just said, let's arbitrarily say it's a positive charge that's being transferred. And we have him to thank for our convention as to, like electricity. In electricity, it's the motion of positive charges. It's what we call electric current, when really it's electrons going the other way. Okay, so let's try some other things. I have a plastic rod here and some rabbit fur. Oh, I can hear this crackle. I know I'm transferring electric charge. It's quite a noticeable crackle. Let's try to figure out what charge I have. I'm going to suspend it in that hanger, and let's take one of our balloons, which I know has a negative charge. And do we have attraction or repulsion here? Anyone? Repulsion. So if this is a negative charge, what charge is now on that plastic tube?
Negative.
Like charge repels, opposites attract. Is this attracting? No. So it's the same charge. So this also must have a negative charge to it. Let's try something else. I have an acrylic rod, and let's try rubbing it with silk. I think this is silk. And is that an attraction or repulsion? Anyone?
Attraction.
Yeah, it looks like an attraction to me. I can actually make it stop and turn around. If I bring it close. So if that black tube has a negative charge, what charge is on this acrylic tube or rod?
Positive.
Positive. What should it do to a balloon then? Any thoughts? Louder? Yes, it is attracting. Okay. So I've got a lot of different objects here we can play around with, but I'd like to try this pop can, which I had laying on its side over here. Okay. Let's take the positive rod. Is that attracting the pop can or repelling it? Okay, what charge do you think is on the pop can?
Negative.
Okay, if this is positive, maybe that has a negative charge. If it has a negative charge, what should the balloon do to it? Interesting. It is attracted to both the pop can and to the balloon. I'm sorry, the pop can is attracted to both the balloon and the acrylic rod. What does that tell us?
Got a neutral charge.
Yes, it can have both charges. And this is metal. Charge is free to move. It's a conductor. So try to imagine how something would behave if the charges inside it could move around. When we bring the positive charged rod nearby, electrons in this pop can are going to be pulled towards it. They're going to move to the side of the pop can that's nearest to it, leaving a positive charge on the other side of the pop can. So the net charge of the can is still neutral. It has just as much positive charge and negative charge, but that charge is redistributed itself. We get negative charge moving over here, positive charge is left over here. And this electric force gets weaker with distance. Remember that d squared on the bottom? That's the separation squared. So even though we've got equal charge on the near side and far side, we have a stronger force from the charge that's closer to the rod because the d is smaller. The charge that's farther away, well, that's something larger squared. That means we have a smaller force. And same thing, when we brought the negative charge balloon nearby, a lot of electrons in this pop can move to the other side of the pop can, farther and farther away. And yes, they're pushed, but that push is weak because that charge is farther away than the positive charge that's left on the near side. And that charge is attracted, and it's a stronger attraction because it's closer. So we say that the pop can was polarized. The charge moved around. It's separated into what we call poles. And we can see that in a lot of different things, not just metal objects, because almost everything around us has molecules that are polar in nature, meaning molecules normally are neutral. They have just as much positive charge as negative charge. But how that charge is distributed throughout the molecule is different. You might have one end of the molecule has more positive charge and another end that has more negative charge. And this is where the little football with plus and minus would have been nice. I did mention that, I know. Do you know where it is?
Yeah, I should.
Okay, if you could, it's got the plus and minus on either side. And so molecules will tend to orient to an electric field if they are polar. And you see this behavior a lot in, well, probably the most noticeable is water. And you could do this experiment at home in your sink. Try to get a thin stream of water going. And you might need to be closer with the camera for this to show up. I don't know. But if we bring a balloon nearby, you see the water stream being pulled towards the balloon? Water is electrically neutral, but it's polar. So those molecules are going to want to shift. Say my forearm is a water molecule, and the fist is a positive charge, and my elbow is a negative charge. Well, bring the balloon nearby, the positive end is going to be attracted towards the balloon, and the negative end of the molecule is going to be pushed away. So the molecule will tend to reorient, getting its positive end closer. And so you'll have a bit of an attraction to that molecule because the positive end is going to be closer to the balloon. But, like this. One end positive, one end negative. Oh, that's kind of like a molecule. So with a balloon, the molecule will want to flip like that. But really, the molecules don't flip all the way around. They might just twitch just a little bit. But if billions and billions and billions of molecules all twitch just a little bit, the net effect is have a shifting of the charge inside the material. So that's why we have the water stream deflected. And if I bring the positive charge nearby, now let's see, let's rub it with the silk again, just in case we lost some of that charge. You can see it's attracted as well. So neutral objects tend to be attracted to anything that has a charge because they're polarized. In this case, we've got the negative end of the molecule wanting to be attracted towards the rod. And so it shifts also a little bit, making its negative end closer, positive end far away, we get an overall attraction. Okay. And water is a very polar molecule, so we see this quite readily. Let's see, do we have the wet and dry cloths? I still need those. Well, let me show you something else. This is another experiment you can do at home. Take some regular cellophane tape and tape a strip it to like a table surface. And basically you have kind of adhesive between the tape and the surface. And if we rip that tape off, well, you see that? It's attracted to me. I told you I was attractive. So we have clearly a charge going on there. And I'm in touch with the ground, so whatever excess charge I get, I'm going to lose very quickly. So I'm essentially neutral. And so that tells me that this strip is most likely charged. Because, yeah, that would work great. So let's take the negative charge balloon, and you see it's pushed away. This tells us that that charge, the charge on the tape, is negative. If it was attracted to the balloon, that would either tell us that the tape was charged positive or it was neutral. You see the distinction? If things are attracted, that tells you that one of the objects is charged. So it means that you could have two objects that are of opposite charges, or one charged of either sign and the other one neutral. But the fact that this is repelled tells us clearly that this tape is charged and that it's charged negative. Take the clear acrylic rod and Braden, could you hold this just with your fingertips up there? I need more hands. Problem is, every time I set this rod down, it could lose some charge. And it also loses, anything loses charge to the air. So bring that close. Oh yeah, look at that. Definitely an attraction. So that tells us that either one of these is charged and the other is neutral, or that they in fact are opposite charged. But since we know that the tape is charged from our experiment with the balloon, that's another indication that this is charged, and it's charged opposite or positive to what we know the tape is. Now, something else we could do is put down a piece of tape. And this is also another cool experiment you can do at home. But I'm putting another piece of tape right on top of it. So I have two pieces of tape, one on top of the other. And if I pull them both off the table, well, I can be confident that they then have a negative charge. Yep. But I want to get rid of that charge. So I'm going to rub it with a damp cloth. I made my tape a bit longer than I probably should have. So, odds are, I took away that charge, and I don't see a repulsion, but I see a slight attraction, which is consistent with this now being neutral. And with our clear rod, yeah, maybe I don't have all the charge off of it. Yeah, it looks like a slight attraction, which also is consistent with it being neutral. So we have no net charge here. But now, if I pull the two pieces of tape apart, they are clearly attracted towards each other. And let's see. These two pieces of tape are repelled. They have the same charge. And we know that's negative, so that tells me that this is negative as well. And this one then, attracted. Either it's neutral or it's positive. And you can hold that. So Braden has both neutral pieces. Balloon, it's attracted. Acrylic rod, it's repelled. So this has a positive charge. So another good example of electrostatics is using pieces of tape. Okay, that's probably good. It could be joked. So let's bring up a PowerPoint slide if we could, please. Question?
Oh, sorry, that was a stretch.
That was a stretch, okay. So electric charge can be transferred when you touch two objects together. If something has extra electrons and it touches something else, well, it could give electrons to that other object. Okay, we need the source set.
I just said it.
You did? Okay. Okay, here's a question. 3 pith balls, basically balls of things that are really good at transferring charge. That's what a pith ball is. Are suspended from thin threads. Various objects rubbed against each other and then touch the pith balls. It's found that balls 1 and 2 repel each other, and balls 2 and 3 repel each other. Did I read that right? 1 and 2 repel, and 2 and 3 repel. Okay, from that, how can 1 and 3 interact, or what can you say about their charge? I got 5 statements here. 1 and 3 carry charges of opposite sign. 1 and 3 carry charges of equal sign. All 3 carry charges of the same sign. One of the objects must not have any charge. Or E, we need to do more experiments to determine the sign of the charges. So basically, what can we conclude from these observations? Think about this for a bit, please. Do this if you need more time. If you're online, type in time in the chat. Does anybody need more time?
Doesn't look like it.
Okay, folks, show me your cards. What do you think is going on here? Okay, what's it look like on the chat?
Well, between B and C.
Okay, any D's or E's?
Nope.
Okay, there are no D's and no E's, but we have A, B's, and C's. Could I get a volunteer to defend A, why A would be correct? But 1 and 3 must carry charges of opposite sign. Could someone volunteer to defend that? Ma'am?
I thought if 1 and 2 repel, then it would, one of them would either be like a positive charge or a negative charge, or one would be neutral.
Okay,
And then I thought if 2 and 2 repel, then that would mean that the first one would probably be negative, and then the third one would be positive, or either way.
okay. So if 1 and 2 repel, that means that either they're opposite charged or one is charged and the other is neutral. And the same would hold between 2 and 3. And that means 1 and 3 need to be opposite in charge.
Yeah.
Okay? What's your name, Miss?
2 and out 1.
Okay. Could I get a volunteer to defend B, that 1 and 3 should carry charges of equal sign? The same.
Yeah, I can do that.
Please do.
Okay, so I thought it was B because if, say, like 1 and 2 repel, or let me put it this way: if 2 and repels both, or attracts both 1 and 3, then 1 and 3 need to have the same charge. But since it repels, it can't. 2 can't be neutral, so it has to be B.
Okay, so 2 cannot be neutral because it is repelled rather than
Right.
attracted. And that means that it's opposite in charge to both 1 and 3. So that means that 1 and 3 must have the same sign charge.
Right.
Okay. Can I get a volunteer to defend that C is correct? That all 3 have charges of the same sign?
I can try.
Okay?
So I was thinking if 1 and 2 repel each other and 2 and 3 repel each other, what repels is the same charge. So essentially, all 3 would have to carry the same charge in order to repel each other.
Okay, so in a way you agree with the last statement, except that if 2 and 1 repel, they're the same charge. 2 and 3 repel, they're the same charge. That means that all 3 have the same charge.
Yes.
Okay, and nobody chose D or E, and I will just state that those 2 are simply not correct. It's either A, B, or C. It's one of those. It's not D or E. So I'd like to hear some discussion between A, B, and C, both online with chats and in the classroom.
I agree with C for pretty much the reasons stated.
Yeah.
Caught myself.
You're like, wait a minute.
Ma'am, what's your name? You spoke up earlier, but I didn't make them up.
Victoria Green.
Okay. Anything on chat?
Jacob Horsley said, I chose C for much the reason that was stated, like charges repel. And then Crystal Scheiss said, I like C the best. I used a picture to determine this. 1 and 2 repel, they're the same charge. 2 and 3 repel, they're the same charge.
Okay, show me your cards, what you're thinking, folks, hit chat. Hit letters on the chat. What do we have on the chat?
Unanimous C.
Okay, that's actually great because C is the correct answer for precisely what the reasons stated. Okay, let's go to the next slide.
We're there.
Okay, yeah, the 2 are really similar. So is there a way to have it so we could, yeah, there we go. 3 pith balls are suspended from thin thread, same thing again. Various rubbing goes on, but now 1 and 2 attract and 2 and 3 repel. What can we conclude now? If 1 and 2 attract and 2 and 3 repel. Can we say that 1 and 3 have opposite sign? 1 and 3 have the same sign, or all 3 have the same sign? Or 1 carries no charge, or E, we need to do more experiments to determine the sign of the charges. So think about this now. And the suggestion of drawing a picture actually is pretty helpful. I'm a very visual person. Drawing pictures helps me out. So that was a good suggestion. So think about this, please. Okay, do this if you need more time. Okay, go ahead and show me your cards. What do we have on chat?
A's and 1 E, it looks like,
A's and E's,
and 1 echo. Just 1.
but everybody's doing A's.
Everybody's doing A's.
Okay. Could I get a volunteer to defend why A is correct? That 1 and 3 carry charges of opposite sign. Could we get rid of that chat?
Yeah, give me 1 second.
A volunteer to defend A, please.
I can try.
Please do.
So I chose A because if 1 and 2 attract each other, then they have to be opposite. And so then if 2 and 3 repel, then they have to be the same charge.
Okay, and so that would mean 1 and 3 are opposite.
Right.
Who's that?
Ashley Wheatley.
Okay. Could I get a volunteer to defend E? Do we need more experiments?
I
Go
can
ahead.
do it.
Oh, wait, a minute, who's this?
Ethan Anderson.
Okay, sir, you go, not Ethan.
Okay, well, I didn't choose E, but I could make a defense for it because we know that 2 and 3 repel, so they have opposite charges. So that means 2 is charged in some way. So 1 could either be neutral or it could be the opposite charge of 2.
Aha,
Therefore, we don't know if it's necessarily opposite of 3. We could possibly need more testing.
okay, because the possibility for, since 1 and 2 attract, we know that 2 has to be charged because it's repelled from 3. You only get repulsion if things have the same charge. But 1 could either be of opposite charge to 2 and also opposite 3, or it could be neutral. We do not know, is what you're arguing.
Correct.
Okay. So nobody chose B, C, or D. I'm just going to say that those are not possible. It's either A or E. I'd like to hear some discussion.
I think I'm gonna change that.
A.
Say, defense for it.
Makes the most sense to me because an object that has a neutral, no charge, can be attracted to an object that has charge, and we have already determined that 2 has a charge, so it can have neutral charge or opposite charge to 2.
Anything showing up on chat?
Not yet. We had Ethan Anderson.
Yeah, I heard.
Okay, we got something.
Okay, read it loud, please.
A case can be made, a case can be made for E, but I like A the best still.
Okay. Okay, that's probably enough time. Go ahead and show me your cards. Folks, hit chat again. Either A or E.
People pretty much stuck with their answers. 1 E, the rest are A's.
So no.
No change.
Okay, it's interesting. We had a complete conversion in the class, a unanimous consensus of E, and yet no change on the chat. Well, still, we had a large number of folks switch to the correct answer, which is E here, and it's correct for exactly the reason that was stated. In that we do know the charges 2 and 3 have to be opposite, but 1 and 2 attracting each other only tells us that they are either, that 1 is either charged opposite to 2, which means it would also be opposite charge to 3, which would be the case A, or it could be neutral because it's attracted to something we know is charged. So we cannot say that 1 is the same charge as 3 because there's a possibility that in fact charge 1 could be neutral. So the correct answer here is E, in that we need to do more experiments. Okay. Let me show you something else that's kind of interesting. I have here something called an electroscope. And I'm thinking maybe I'm going to move it over here so it's closer to the people in the classroom. And we might have to move the laptop so it's closer. And what I have here is I have aluminum foil ball connected by some baling wire down to a hook that supports 2 strips of aluminum. And the 2 strips of aluminum are kind of free hanging. If I rub a balloon in my hair, this has a negative charge, bring it close. You see that the 2 aluminum strips are pushed apart. Can everybody see that okay?
You guys still see with this?
Mr. Bobak, or can you see it from back there?
Yeah.
Okay. That's with the negative charge. When I bring a positive charge nearby, I need more positive charge. Okay, I'm not quite getting what I was hoping. I'm going to break out the big guns. Plastic wrap. Plastic wrap is very staticky. That's why it's so good at clinging to things. And the plastic wrap really, really likes electrons. It'll strip electrons away from just about anything. And to show you that, I've got the balloon that I know is negative. Wait a minute. That was strange. That's not how I expected it at all. Yeah, it's clearly charged. That was weird. I was expecting this to have a positive charge. Okay, I'm going to try to go back to the silk, because I know I got a positive charge with that. Okay, so at least I got some charge now. So this has got a positive charge. And you can see it makes the leaves go apart. The little pieces of foil separate as well. So this tells us that something's charged. It does not tell us what that charge is. When I bring the balloon nearby, this is all metal. The aluminum foil and the wire is metal. So electrons are going to try to get as far away from this balloon as they can. They're going to get pushed down into those strips, which is going to make those strips both negatively charged and they're going to push away. When I bring the positive charge rod nearby, electrons are going to be pulled towards this rod. They're going to be sucked up out of those aluminum strips, leaving them with a positive charge, and so they'll push apart. So this tells us something's charged, but not what charge it is. But if I were to bring this close, so we get a separation, and then touch the other side of the ball, you see how the strips go close together? And now when I remove the balloon, those strips, let's do it again. That's not as much of a separation as I would like. Okay, now the strips are repelled from each other. That tells us that this scope now has a net electric charge. And let's try to find out what charge that is. If I bring the positive charge rod nearby, the strips got a bit closer. When I bring the negative charge, that's not what I expected. This is what I expected. So when I bring the negative balloon close, the strips get close together and then they get farther apart. And when I bring the positive rod nearby, they get farther apart still. Okay, that's what I expected. So that tells us that these strips, if they got farther apart when I brought the positive rod nearby, they got farther apart when we removed more electrons from them. That tells us that they are a positive charge. This has a positive charge. And when we pull more electrons out of those strips, they get even farther apart. When I bring the negative charge rod nearby and I push electrons into those strips, they go together. So when I bring them close, the strips are now neutral because I push more electrons down into them. And if I bring this even closer, I'll push so many electrons down into them that they'll repel again. Do you see that? Or they go together and then they go apart. You see that? We charge this thing by induction. That's what happened. By bringing this close and then touching the opposite side, electrons want to get as far away from this balloon as they could. Some of them escape to my finger, leaving this with fewer electrons and therefore a positive charge. So now that we charge this, we can determine what other charges are. You know, what something has a charge, because it'll behave differently as to whether or not we bring something positive nearby or something negative nearby. So this is another way of charging something without actually touching it to something that's charged. We touched it to something neutral so that charge could escape to it. Does that make sense to folks? Okay, so let's do the next slide, please. Okay, so here we have two uncharged metal balls labeled X and Y, and a third ball carrying a positive charge, ball Z. So we have ball Z, no association with dragons whatsoever, is brought nearby. And then we have a wire, a conducting wire, a piece of metal, connects X and Y. It's then removed, and then ball Z is removed. What do we have as far as charge on balls X and Y as a result? We didn't actually have any physical contact with ball Z to either X or Y, but we did have a connection briefly between balls X and Y. So which of these statements is correct? Are X and Y still uncharged? Are X and Y both positive, or X and Y both negative? Or X is positive, Y is negative, or X is negative and Y is positive? Pretty much all possibilities are covered here. Think about this question for a bit, please. Okay, we're running short on time, so I'm going to call discussion to a quick close. Go ahead and show me your cards. What's it look like on chat?
3 A's, 1 D, 1 E.
3 A's what?
1 Delta, 1 Echo, 1 Baker.
So no C's?
No C's.
Okay, so we've got everything except for a C. And I'm looking at my watch and we're just about out of time. So stay tuned. I know this is leaving you all in horrible suspense, but we'll come back to this question first thing tomorrow morning. Thank you for your attention.